Hello everyone, welcome to the third lecture of the series of feedback amplifiers. Today we are going to discuss about the voltage series configuration specifically, and we will see how we can define the input impedance, output impedance with respect to feedback. Commonly they are known as RIF, ROF, and we will see how they can be derived. In last two lectures, we came to know that what are the types of different feedback amplifiers, what are their basic characteristics, how we can configure them, and we have also learned that what is the sampling and mixing networks, and how from the knowledge of those sampling and mixing networks we can configure the different types of feedback amplifiers. So today the topic of discussion will be on the voltage series configuration, and we'll be discussing about the input impedance with feedback, output impedance with feedback, output impedance with the load resistance RL, and what will be the outcome. I'll discuss it later, and the questions related to this particular lecture. So starting with the discussion, voltage series configuration, or popularly it is also known as voltage amplifier. Why, we have already discussed in the previous two lectures, but to revise with the what we have learned already. This is the output circuitry, and this is the input circuitry, and as I have told you in the second lecture that always bifurcate these terms into two parts, first part and the second part. When we are talking about the first term is giving me the knowledge of the voltage, and when the first term is defined, we are discussing about the sampling, and sampling is done at the output. These things we have to remember. Second term is written over here is the series, so we are interested in the concept of mixing, and mixing is done at the input side. So we are sampling the voltage. So sampling of the voltage is done. What kind of sampling network we required, as we discussed in the previous lecture? The sampling network of the voltage should be of a parallel kind, of a shunt type, and it should be mixed. It should be mixed with the voltage source Vs in series type. And when we are mixing in it with the source voltage, then it has to be mixed in the form of the voltage. So this is voltage is sampling and voltage is mixing. And as I already told you that sampling and mixing have opposite concepts, so we keep remember this concept, and we will will be applying these concepts in all types of configurations. To start with, this is the output V0, this is the input Vi will be again Vs minus Vi will be again Vs minus Vf, so voltage upon voltage, so gain will be Vo upon Vi. And this thing we have discussed in very first lecture, that what should be the ideal characteristics of voltage amplifier. So voltage amplifier would have Ri greater than Rs, because we want all the voltage has to be appear across the input impedance of the transistor only. And since we are interested to take the output across the load resistance, hence the load resistance value must be on the higher side. So this gives me Ri must be of a greater value, and RO must be of the least value, practically talking about. So we will be discussing that how this network is how this network is important, and why, and how we can derive the RIF and ROF values. So input impedance with feedback. So look at this input circuitry, and this is the output circuitry of the voltage amplifier. So what is the addition with respect to the first lecture? In first lecture we have drawn the voltage amplifier, but there we have not mentioned this feedback element, because there we have not considered the feedback topology. There we have just defined that what kind of feedback amplifiers we can have and how they can be configured. So here I have drawn the VF is nothing but the feedback voltage that comes from the feedback network, as we have seen in the previous lectures as well. In the previous slide I have drawn the feedback network. And since we are interested in series kind of mixing, then this voltage source is in the series with the VF is the voltage which is coming out from the output. And always remember, students, when we are drawing the VF, we should remember that the polarity of the VF is such that it should oppose the polarity of the VS. Why I am saying this? Because we are talking about the negative feedback of the amplifier. So if the feedback is negative, then it has to be Vs minus Vf. It cannot be Vs plus Vf. If it becomes Vs plus Vf, then it will convert into the positive type of feedback. So in this particular feedback amplifiers unit, we are talking about the negative type of amplifier. And when we talk about the negative type of feedback, then we have to be very sure that Vf must be applied so that it should oppose the polarity of the Vs. So likewise, how you can find out that this is the II, this is the input current which is flowing across this loop. So it is entering towards the from the minus terminal of the voltage, and here it is entering towards the plus terminal of the voltage. So we can say that Vs and Vf are in the opposite polarity. So this is the RIF equation. RIF is the input impedance. Input impedance must be defined as the input voltage upon input current. So what is the input voltage? Input voltage means the source voltage here. Input voltage means the overall source voltage of the amplifier. This has to be remembered. So Vs, because we are talking about RIF, we are not talking about RI. If we talk about RI, then it should be the input impedance should be defined as Vi upon II, because we then define in terms of the transistor's input only. But since we are talking about input with feedback, RIF, this is very important, then we have to consider the source voltage Vs as the voltage source, and II is definitely going to be the input current. So Vs upon II gives me the basic definition of RIF. This is the our equation number 1. And when we apply KVL at input loop, we can easily determine that Vs minus this particular drop II upon Ri minus this particular voltage which we have got from the feedback Vf equals to 0. Summation of the voltages equals to 0 as per the KVL rule. Why we have not considered the drop across this Rs? Because we have ignored the value of the Rs as per the basic fundamental characteristic of the voltage amplifier, what we have seen in the previous cases, what we have seen in the previous lectures as well. Ri must be greater than Rs, or practically Rs is very low kind of value. So we can ignore Rs here, and we can write this equation without considering the value of the Rs. Again, this is the just the Vs equals to Ri plus Vf. And what is this Vf? Vf, it is nothing but the feedback which is coming from the output, and we can see that the output circuitry is the voltage circuitry, so it has to be in the form of voltage only. So this Vf, which is the feedback voltage, it is coming out to be beta into V0, and V0 is nothing but the output voltage of the amplifier. So we are sampling the output voltage through our feedback network, and this beta is the feedback factor which is defining me that what quantity I am interested in to sample the voltage from the output side and feed it back towards the input side, that is the Vf. So this is the relationship, and we can give it as equation number 2. And now we are interested to know that how we can define this V0. Why we are interested in that? Because this is the only quantity which relates me to the output terminal or output circuitry, because Vs is at the input side, II and Ri is the input side, beta is the feedback factor. Only V0 is the element in this particular equation which is coming out from the output network. So we should go to the output network and see what kind of relation V0 shares with the Vin or with the input circuitry. Going ahead, so V0, as we know that V0 is nothing but AV into Vi. What is AV into Vi? If you consider the previous slide, this is the voltage source, and voltage source is divided into two types of resistances, RO and RL, and we are interested to have or to consider the V0 across the RL and not across the R0. So if you remember the voltage division rule, it clearly gives me that if I am interested to calculate the V0, it should be the source voltage multiplied by the RL, that is the load resistance, where we are interested to calculate the V0, upon the combination of the two resistances R plus RL. As simple as that. And from here we can calculate V upon VO upon VI, V0 upon VI. V0 upon VI may be defined as AV dash, and AV dash is nothing but we have defined a different constant to represent this particular variables, and AV dash can be written as this. So or V0 can be written as AV dash into VI, just to replace the value of V0 which we have considered in case of equation number 2. So from equation number 2, which we have seen in the previous slide, we can easily write that Vs is nothing but Ii into Re. This is the same beta, and this is how we have replaced the value of the V0. V0 is nothing but AV dash into Vi. And what is Vi? What is Vi? Vi is nothing but Ii into Ri. So this equation again becomes, we have replaced the value of Ii, and Ii is common. This is Ii into Ri is common. Here it is common, so we are taking the common out. And since we know from the equation number 1 that we have to find out Vs upon Ii, we have to find out Vs upon Ii. So in that proportion, or taking that thing into account, I should be finding out the value of Vs upon Ii. So Vs upon Ii gives me the value of Ri into 1 plus beta AV dash. So ultimately this equation 3 which comes to the slide, which gives me the relation that RIF is nothing but Ri into 1 plus beta V dash. Now what does it mean? It means that when I am taking the feedback and I am interested to calculate the input impedance with feedback, then Ri it gets multiplied by this particular factor 1 plus beta AV dash. So RIF is greater than Ri by which quantity? By this particular quantity which I encircled. So input impedance, what is the outcome? Input impedance of amplifier with feedback increases when connected in a voltage series configuration. And this particular term is known as desensitivity of the negative feedback amplifier. So this desensitivity we'll discuss in some other lecture, why this desensitivity is important. To just have replacing this as a constant here, so we can say that RIF is the Ri into D. So RIF increases by the factor D if we apply the feedback in voltage series configuration. Moving ahead, let us discuss about the output impedance with feedback. So now we are interested in the output circuitry. So this is our output circuitry, and we want to find out ROF. ROF must be VO upon I0. And if you remember the Thevenin's circuit, or if you remember the calculation of output impedance, you should also remember that whenever we are talking about the output impedance, then the voltage source must be turned off, or the current source must be turned off. Since it is a voltage source, we are shorting it. If it would have been a current source, we have opened it. Why we short the source voltage or source current? In order to calculate the RL. So if you remember the low frequency amplifier analysis, when we calculate the Y0 value, that is the output admittance value, we have shorted the we have shorted the input source, because we do not want any interruption or any kind of intervention from the input circuitry, or any kind of contribution of impedance from input to the output. So we want that the source voltage or source current must be disconnected from the circuit, so that when we calculate the R0, it should be the pure value of output impedance only. So here we are interested to calculate ROF. I have just separated to have a feel of a two-port network. The two-port network very well. So this is the RL, that is the load impedance, and we are interested to calculate the ROF. So this is the I0 which is flowing across the RL, and I have considered another current which is known as I0 dash, which is just opposite of the I0. Okay, now this is the KVL at the output loop. So when we apply the KVL at the output loop, we get to know this particular equation, and just by manipulating the values, I have calculated the I naught dash. I naught dash is nothing but equation number 2. And now this is the very important, from input loop we can see that since Vs is equals to 0, Vi plus Vf equals to 0, because there is no source voltage. So Vi can be written as minus Vf. Why we are interested to calculate the Vi here in terms of feedback? As we have done in the previous case, while calculating the input impedance, we want some value which which was dependent on the output circuitry, and in the previous case it was the value of the voltage V naught. And here in this case, the relationship in equation number 2, we can see that Vi is the term which is reminding me the circuitry of input, and whatever Vi which is available across the input, that has to come across the output in order to calculate or in order to solve the equation number 2. So Vi here it is represented in terms of the feedback voltage, and by equation we can easily write Vi equals to minus Vf. So just we have put it down here. Vi equals to minus Vf, this minus minus plus, and we very well know that Vf equals to beta into V naught. So we have replaced the value beta into V naught here, taking V naught common, I naught upon V naught. What I naught dash upon V naught gives me? It gives me the value of the admittance, current upon voltage. I want to calculate the impedance, so I just have reversed this value. So V naught upon I naught dash can be written as Rho upon 1 plus AV beta. Now this is the equation number 3, which is very important. And what conclusion gives to me? It gives me the conclusion that ROF equals to Rho upon D. D is the same sensitivity factor as we have discussed in the previous case. So the outcome is ROF decreases by this quantity of D. So ROF is less than RO by this quantity D. So when we connect the voltage series configuration of feedback amplifier, then we get the lesser value of the ROF as compared to the original value of the R naught in case of the transistor. So this is nothing but ROF dash when we are considering the value of the RL also. So ROF dash can be found as the parallel combination of ROF and RL. So you can go through the slide. This is just the equations, and at last we define the value of the constants RL dash and AV dash, and this is how we get to calculate the value of RIF and ROF. So what are the outcomes of today's lecture? Outcome is the sampled signal. In case of voltage series configuration is voltage, we are sampling the voltage, and we are feedback signal is also the voltage. And I'm saying the feedback signal is the voltage, what kind of mixing we are using, that comes into account, because we are mixing it in the series, so it has to be the voltage. If we are mixing it in the shunt, it has to be the current. So the sampled signal is also in the form of the voltage, and since we are series mixing, we are considering the series mixing, it has to be the voltage of the feedback signal also. So voltage and voltage from both the end. Another important configuration, input impedance with feedback increases, RIF increases here when we connect it in the feedback of the voltage series, but ROF reduces. So RIF is greater than RI and ROF is lesser than RO. This is the important conclusion. Why RIF, ROF or input and output impedances are important to consider? Because in any kind of analog network or in any kind of electronic circuitry, it is very important to know what are the impedance characteristics of that particular electronic circuit. Because when we are connecting number of electronic circuits in a cascade or in cascade configuration, then if you are not knowing the input and output impedances, it may lead to the hazardous condition. Because if we if you don't correctly determine the value of the current which has to be driven out, or which has to be fed back, or which has to be applied at the input of the electronic circuitry, in terms of getting the value of the impedances, then it will turn out to be the unpleasing conditions in the electronic circuitry. So what kind of questions we can expect from this particular slide? That you can be asked to draw the configuration of voltage series. This is very general question, but what can be the twist? They can ask you that draw the particular circuitry and determine the value of RIF, ROF and ROF dash by knowing the value of the basic characteristic. And what is the basic characteristic of the voltage amplifier? It has to be the value of highest of RI, and it has to be the lowest value of RO as written over here. So as we have considered already that Ri must be greater than Rs, and Ro must be less than Rl. So this particular amplifier can be acts like this. So determine the value of the RIF ROF, which have the highest value of Ri and lowest value of R0. So likewise, you can go through the analysis, and it is very important to go through the first and second lecture in order to understand what we have discussed in this particular lecture. Thanks for watching.